Others are coming. Please come front. Don't sit at the back. Come here. Come to the front room. The Zoom பண்ணிடு. First Zoom பண்ணிடு. இந்த ஃப்ரேம் தான் கேட்குறேன். இது கரெக்டான ஃப்ரேம். வைஃபை ஆன் பண்ணிடு. வைஃபை ஆன் பண்ணிடு. ஆன் பண்ணியாச்சா? Those are online are able to hear me?
Yes, sir.
1 minute. Yeah. So shall we get started? Listen. So till now, the concepts that we were discussing is right. So till now, what were the concepts that we were discussing? We were concentrating on when a current carrying conductor is given, whether it is a straight current carrying conductor or a circular current carrying conductor, how is the magnetic field generated due to this? So for straight current carrying conductor, we found a value. For circular, we found a value, right? Now the next question is exactly the reverse of it. In the sense, instead of we creating the magnetic field with the help of, listen to this carefully, instead of we creating the magnetic field with the help of moving charges, what will happen if a moving charge is entering an already present magnetic field? In the sense, what is happening? So initially what was happening is current carrying conductor was producing the magnetic field. Now what is happening is this magnetic field is already present. In this magnetic field, you are putting this charges into motion, right? So when you do that kind of an operation, then there is something called as force that is going to get generated on a charge which is moving in a magnetic field. Okay, and that is what we are going to concentrate on. So listen to this. The topic is going to be force on a moving charge in a magnetic field. Right. So what is happening in a magnetic field? There is a charged particle projected, and we are going to calculate what is the force experienced by it. Okay. Now, let's say there is a magnetic field existing of magnitude B. Okay. See, the one I have drawn here is a uniform magnetic field. Since our discussion is going to be mainly restricted to uniform magnetic field, I took that itself into consideration. Okay. So into this, what you're doing is you're taking a charged particle of magnitude Q. I don't know whether it is positive or negative charge. I took a charged particle of magnitude Q. I am going to project it, let's say, with a velocity V, right, at an angle theta with respect to the magnetic field. Then what happens as soon as this charged particle enters the magnetic field is it starts experiencing a force, right, which is observed to be directly proportional to the magnitude of the charge that is pushed into it. Secondly, it is directly proportional to the velocity with which it was projected with. And it is observed to be directly proportional to the magnetic field strength into which it is projected. And it is also proportional to the value of sine of the angle between the velocity vector and the magnetic field vector. So this is a magnetic field vector, velocity vector. So if you take the angle between them to be theta, then we take sine of that angle, and force is dependent on all these four quantities. In which way? In the directly proportional. Okay. So when it is directly proportional, when you combine all these things, then F is observed to be directly proportional to Q V B sine theta. So if you remove the proportionality constant, the constant that is going to come is 1. So everything was experimentally observed. So the constant of proportionality is 1, and you write it as Q V B sine theta. If you observe, everywhere I have written in terms of scalar quantities. We know that force is a vector quantity, velocity and magnetic field are also vector quantities, but everything I wrote it only in terms of scalar quantity. So this is going to be the magnitude of the force that is experienced by the charged particle. What is this? This is going to be the magnitude of force experienced by the charged particle. Am I clear with this? Now, the question is, since force is a vector quantity and velocity and magnetic field are also vector quantities, I have an operation of the product of magnitude of two vector quantities and sine of an angle between them. So what is the vector operation I can think of between these two? Obviously, it is cross product. So when you write it as cross product, that is, if you write the force as a vector quantity, it is given as Q multiplied with the velocity vector cross B vector. So it is given as F is equal to Q into V vector cross B vector. It is not the reverse. So have that in your mind. It is Q into V vector cross B vector. And this is going to be the force experienced by whom? By the charged particle projected with a velocity V at an angle theta into the magnetic field of intensity B. And this force is called as the magnetic force. You can write it as M as the subscript. Okay, generally, when you think of a charged particle, we can think of electric field also. So electrostatic field is represented with the symbol F with a subscript E. If it is magnetic force, you can, electrostatic force is represented by the symbol capital F with E as a subscript. Here you can write capital F as M as the subscript. Is it clear? Okay. So this is the value. You can make a note of it. ஸ்லோவா மூவ் பண்ண சொல்றேன். இன்னும் கொஞ்சம் மூவ் பண்ணுவோம். Okay. Yeah. So this value being the magnetic force experienced by the moving charge in magnetic field. Now we will discuss about a force which is called as Lorentz force. So now what I described is actually a concept of magnetic force experienced by a charged particle. If suppose there is a charged particle, right? If suppose there is a charged particle which is moving in the presence of electric field and magnetic field. If suppose there is a charged particle moving in the presence of electric field and magnetic field, then the resultant force experienced by this particle is given as the vector sum of the electrostatic force and the vector sum of the magnetic force. Okay. So here, what you can do is you can either write it as Fm or you can also write it as Fb. See, both are same. Okay. So I wrote it as Fe vector plus Fb vector. So this I can write it as Q into E vector plus this can be written as Q into V vector cross B vector. So what is going to be common among both? The scalar quantity Q, if you take it out, it can be written as E vector plus V vector cross B vector. And this is what is called as the Lorentz force. So Lorentz force basically speaks about the combined force that is acting when a charged particle is moving in the presence of both electric and magnetic fields. So what you can say is the previous force that we have written here, Fb vector is equal to Q into V vector cross B vector. You can also call it as Lorentz force for magnetism. Okay, what do you call it as? You call it as Lorentz force for magnetism. Remember, Lorentz force mainly speaks about the combined force, but mostly what happens is we don't take the electric field into consideration because in this chapter we are concerned more about how the magnetic field is affecting the charged particle. So we will take only Q into V vector cross B vector. That is why in all the derivations going forward, we'll be using only Q into V vector cross B vector, which we call it as Lorentz force for magnetism. So have that in your mind registered. Okay. It's not placed, it is moving. If it is placed, then V vector will be 0. No? Placed means it is at rest. Electric field, whether the charged particle is at rest or in motion, it will experience force. Okay, you will understand after I discuss these two cases. Okay, so don't use the word placed, it is moving. Is that point clear? Shall I proceed? Did I use the word placed by any chance? No, no. Okay. So listen. So the next question is how to find the direction of the force experienced by the charged particle. Right. So how are you going to find the direction of force experienced by the charged particle? One way is you can directly use the concept of cross product of vectors and use this v vector cross b vector and tell the direction. But here you need to be careful. See, f vector is equal to q into v vector cross b vector, right? So I'm just giving you a lead before understanding why we need Fleming's left-hand rule. So concentrate on what I'm trying to say. So when you do this v vector cross b vector, you get a result and say your force is also in the direction of k cap, right? So that's what we can conclude, right? But that's wrong. Magnitude of charge is important. I mean, the nature of the charge is important. Suppose v vector cross b vector comes out to be k cap, you cannot conclude that the force is in the direction of k cap. The force is in the direction of k cap only if the charged particle is positive. It is in the direction of minus k cap if the charged particle is negative. So you need to have the presence of mind. Okay, so you need to ask this question even before you write the answer. Now the next question that we need to answer is there a direct way, is there a rule that can actually help us to find without using the cross product of vectors? And the answer to that is Fleming's left-hand rule. Okay, so what does it state? It is not Fleming's left-hand thumb rule or something. There what we discussed is right-hand thumb rule because thumb was playing an important role. So we use only thumb and the right hand. Here, why we call it as Fleming's left-hand rule is we are going to use 3 fingers. Okay, so one point that needs to get strongly registered in your mind is whenever you're doing cross product of two vectors, I am stressing on this point, concentrate. Whenever you're doing the cross product of two vectors, the resultant will always be perpendicular to both the vectors for which we are doing the cross product. Meaning, if I have velocity vector in one direction and magnetic field in another direction, force will be in such a way that it is perpendicular to both velocity and magnetic field at the same time. That is the meaning of cross product. So from that idea, what we can take is the concept of placing 3 fingers mutually perpendicular to each other. That is where the idea comes from. Are you able to understand? So what we are supposed to do is stretch the thumb of and the first 2 fingers of the left hand. So if you want to find the force, what are you supposed to do? You need to take the thumb, the forefinger, and the central finger. They need to be stretched mutually perpendicular to each other in such a way, what is going to happen? Forefinger is there, no? So forefinger should be pointed in the direction of field. Which field? Magnetic field. Forefinger should be pointed in the direction of magnetic field. What about the second one? You have the central finger, right? So when you talk about the central finger, remember it starts with C. So it should be in the direction of current. But here, sir, you're talking about charge, right? So when I talk about current, current is the direction of flow of positive charge. Current is the direction of positive charge, right? And the thumb, it starts with T, in fact, TH. the thumb should be in the direction of thrust. Thrust means basically force. So remember it like this. Forefinger, the first word starts with F. Sorry, the first letter starts with F. So forefinger represents the direction of field. Central finger represents the direction of current, C and C. Thumb represents the direction of thrust. Okay. Having said this, if I take magnetic field to be in this direction, right? If I take velocity to be in this direction, where it is perpendicular to each other, I'm just taking it only for the sake of understanding. So when I put the velocity in this direction, right, the first question that you need to ask me is whether I'm talking about a positive charge or a negative charge. Okay. Here I'm assuming that the charge is positive. Okay. So there is a positive charge moving in the y direction. There is a magnetic field in the positive x direction. So first let's apply this concept and see. So for me to find the direction of F vector, what should I do? Q into what is the value of V vector? V vector is the direction of J cap cross what is the direction of B vector? I cap. So what is J cross I? Minus K. So I will write the answer as minus K cap because the charge is positive here. Right? That's what cross product tells me. So let's validate using this thing. Okay. So here, out of the three fingers, I would suggest don't stretch everything at the same time. Okay. Stretch them one by one, adjust the position, and then stretch the last one. So the last one should be the unknown one. Here, if you know, what are the two known parameters, velocity and the magnetic field. So velocity is the direction of current. So you know the direction of current and you know the direction of field. So you know the direction of these two fingers. Okay. First, extend your forefinger, place it in the direction of field. Okay. Then extend the central finger, adjust it in such a way that it is matching with the direction. Okay. When you do this, then you extend the thumb, that will automatically give you the direction of the force. So both are matching. See, my thumb is saying it is into the plane, minus K cap is also into the plane. Okay, did you understand what is the sequence we need to follow? First, always concentrate on the two terms, which are the two directions which are known to you, right? So go one by one among them itself. It is up to you. You can go in whichever order. Generally, it's easier to open with the forefinger. That is why I go with field. So forefinger, central finger, adjust it, then extend the thumb. It is going to be into the plane and you're sorted. Is that point clear? Yes. Right? So this is all about the concept of Fleming's left-hand rule. So I hope you are clear with understanding how to relate the cross product. At the same time, use this also. So in a problem, if you get stuck with either of them, you will be able to solve it on your own, right? Current should be considered downwards. See, had they given negative charge, forefinger, central finger. So since upward is the direction of current, sorry, downward is the direction of current, you'll put it like this, extend the thumb, this is the direction of force. Done? Shall I proceed? See, now we discussed that F is given as QVB sin theta, right? F is given as QVB sin theta in terms of scalar quantity, right? So from here, if I take the special cases into consideration, suppose I take the first case where the velocity of the particle is 0, meaning I take a charged particle and just put it in the magnetic field at rest. So when I put it at rest, right? So when velocity is 0, if I substitute V is equal to 0, what am I going to get? F will be 0. So what is the meaning of this? So F comes out to be 0 here, meaning that the charged particle continues to stay at rest. So a charged particle still continues to stay at rest itself, right? So this is what happens when the charged particle is placed, right? When the velocity is 0. Now, the next question is, what will happen if the charged particle is projected at an angle theta is equal to 0 or 180 degree? Again, if you look at the mathematical expression, F will be equal to QVB sin theta. In this case, what is happening is velocity of the particle is not 0, right? It is projected. But what is 0? Theta is 0 or 180 is literally putting sin theta to 0. Because sin 0 is also 0, 180 is also 0. When I take sin theta is equal to 0 and put it here, then what is going to be the magnetic force experienced by the particle? It will be 0. Here is where an important question comes. All right. So previous case also I told it is 0. Okay, accepted. But I told that the charged particle continues to stay at rest. So here what is happening? Here also the force is 0. So can I conclude that the charged particle is still going to stay at rest? This is what we need to be careful about, right? One biggest mistake that happens is when we see force is equal to 0, we start assuming that the particle is always at rest. Not necessary. Force will be 0 in two scenarios. When is it? See, force will be 0 only in one scenario. When force is 0, the biggest conclusion you can draw out of this is acceleration is 0 because force is equal to mass into acceleration. But acceleration can be 0 in two scenarios. What is it? When the velocity of the particle is 0 or the velocity of the particle is constant. So what is the meaning of this? Here, the force is equal to 0 doesn't mean that the charged particle is going to be at rest. It will continue the motion in uniformity. In the sense, it is going to have a uniform motion throughout. Now, the next question is, if you project the charged particle with velocity v either at an angle theta is equal to 0 or you project it at an angle theta is equal to 180 degree, right? What will happen is this particle is going to have a uniform motion accepted. But most importantly, the particle will move in a straight line. So you can have a question like this. So you need to project a charged particle into magnetic field, external magnetic field, and you want the charged particle to move in a straight line path. Then how will you project it? So you should not give zero velocity, means you should need to give non-zero velocity to it. At the same time, project it at an angle theta is equal to 0 or 180 degree. This is an important point to be kept in your mind. Is that clear? So these are the two special cases related to the Lorentz force of magnetism. Make a note of this. And copy this. Done? Go close. உள்ள இருக்காரு. Okay. Yeah. Done with this? Yeah. See, this one we saw, no? Motion of a charged particle in uniform magnetic field. You know this. When the initial velocity is parallel to the magnetic field, right here, what is going to happen? Sine 0 will be 0. Hence, it's going to continue to move in a straight line path. See, just for the sake of continuity, I'll write it again. Yeah. So now we will discuss the concept of motion of a charged particle which is strictly restricted only to uniform magnetic field. Okay. So when you talk about this, when the initial velocity is parallel to the magnetic field, when theta is equal to 0 degree, then what is going to happen to the force acting on it? We know that F is equal to QVB sine theta, but theta is going to be 0. So when you substitute a 0, answer will be 0. So here, what is the conclusion that we can draw? That the particle continues to move in a straight line path. So it continues to move in a straight line path. Right? Now, the next question is, when the initial velocity is perpendicular to the magnetic field. This is a very important concept, right? Most of the problems asked are based on this. Here, unlike the previous scenarios where I considered the field lines to be horizontal, here I considered the field lines to be into the plane. Okay, so here what are we going to do is, if I take this to be the magnetic field of intensity B, right? Let me say there is a charged particle Q which is projected with a velocity V into this magnetic field. So when you project it into the magnetic field, how are you projecting it? V is in this direction, B is in this direction. So how are they both with respect to each other? They both are perpendicular with respect to each other. So when you project them perpendicular to with respect to each other, then what is going to be the force that will act on the charged particle? F will be equal to QVB sine of 90 degrees. I have not yet written it as a vector quantity if you observe. Right? I wrote it as scalar, then I will write it as vector. So F is equal to QVB sine 90, which is going to be QVB itself. Right? Now, if I write it as a vector quantity, in this scenario, tell me in which direction is the charged particle going to experience force. See here, we will go with the cross product of vectors itself. So charged particle I considered as positive. So F is directly proportional to B vector cross B vector. So what is the direction of velocity vector? It is I cap cross. What is the direction of B vector? It is minus K cap. So it is going to be negative of I cap cross K cap. So what is I cross K? So if you take it like this, I J K, I cross K is going to be minus J. Clockwise is negative, right? So it is going to be minus J. So it is going to be negative of negative J cap, which will be J cap itself. So what is the meaning of this? Means the charged particle starts experiencing force in the upward direction. Means as soon as this particle enters the magnetic field, it starts experiencing a force in this direction. So when there is a force in this direction, it will tend to accelerate in the direction. Right? So it is going to accelerate. Okay. Due to which what will happen is, since there is a force which is pulling perpendicular to the velocity, the particle will tend to take a curved path like this. Accepted? It will take a curved path. It will take a curved path, no? Because velocity is like this, force is like this. Right? So what should happen? It is like, if you think of a projectile, for instance, when you think of a projectile, what happens? The horizontal velocity is like this. The force is like this. It is because of which it is taking a curved path. No. In a similar way, if you take the velocity to be in this way and force to be upward, it will take a curved path. But I don't know what curved path it is. I have not yet concluded. But only thing that I know till now is that when I write force is equal to Q into V vector plus B vector, how is velocity and how is velocity and the force? How are they both? They are always perpendicular to each other, in the sense, here the force and velocity are perpendicular. So let's say it has taken a curved path in this way, and at this point, let me say that the velocity is going to be like this. So velocity is always tangential to the surface. So at this point, what will happen is, we know that velocity and force should be perpendicular to each other. In this scenario, the force will start acting in this direction because it is acting inward to this curve. So to this curve, initially it acted inward. Here also it acted inward only. Okay, that is one way. Or else you can apply the Fleming's left-hand rule and check it. So what are we supposed to do? Take the forefinger, place it in the direction of field. It is into the plane. Take the central finger and adjust it in the direction of current and extend the thumb. You are able to see the thumb is going in this direction. Right? Is it matching? It is going to go in the upward direction. So due to this force and this velocity, what will happen? Again, the charged particle will take a curve. So at this point, what will happen? The velocity will be in this direction. And again, logically, what should happen? The force should be in this direction. So are you able to understand what is happening? So from the basic of cross product itself, we know the fact that the force and velocity are, since F vector and B vector are always perpendicular. In this scenario, what is happening? Force and velocity being always perpendicular to each other. Observe, the velocity in this case is going to be a constant y. The speed is going to be a constant of this particle y, because you can change the speed of a particle only when you apply force in that direction. So here force is getting applied in which direction? In the perpendicular direction, but there is no force in the direction of velocity. So this is velocity, this is force. So there is no force to change the velocity. So velocity is still remaining constant, but there is always a force which is acting perpendicular to it. So there is only one kind of a motion where velocity is constant and the force is always perpendicular to the velocity. And that kind of a motion is a uniform circular motion. So here, this is a very, very, very important conclusion to be drawn. So what happens when you project a charged particle perpendicular to the magnetic field? The path traversed by the particle is going to be circular, and the name of that motion is going to be uniform circular motion. So in uniform circular motion, what is the only force acting on the particle? What is that force that is acting in this direction perpendicular to the velocity? It is the centripetal force, right? And the centripetal force is given by the expression mv square by r. In this case, the centripetal force is provided by the magnetic force Q into V into B. So QVB is the magnetic force, right? This is the magnetic force. But what is the centripetal force that needs to keep this in the circular path? It is, okay, 1 minute. So here I put an arrow mark to show you what is the direction, but I've already shown you the direction. So I'm removing this. Okay. Similarly, here also I'm removing this. So FC is equal to mv square divided by r. Let me take this as equation number 2. So 1 and 2 are supposed to be equal logically. Then can I write QVB is equal to mv square divided by r? V and V will get cancelled. So what is going to be the value of R? R is equal to mv divided by qb, and this is going to be the radius of the circular path in which this particle is going to traverse. So as I told you in the beginning of this topic, this is the mathematical equation on which many problems can be framed. Okay. So R is given as mv divided by qb. The next point is, if I look at this expression R, so R is given as mv by qb, no? This m into v is called as linear momentum, which can also be written as p divided by qb. So what is it? It's called as linear momentum, which is represented by small p. So it is p divided by qb. And there is a relation between kinetic energy, which is given as half mv square, and momentum, which is given as mv. The kinetic energy is given as p square divided by 2m. So all that you need to do is square this, substitute it, and then you need to solve it. When you do that, you will get p square by 2m. So p is equal to root of 2m into k. So this can also be used here, which is going to be root of 2m into k, the whole divided by qb. So what happens in a problem is, depending on the parameter that I give you in the question, you can use either of them. If they give you the mass, velocity, charge, and magnetic field, use the first one. Instead of instead of mass and velocity, they directly give you the linear momentum. Use the second one. If they speak about kinetic energy in the problem, then use the third one. But remember, all the three mean the same. Okay. So this is going to be the radius of the circular path. Under what scenario? When the charged particle is projected perpendicular to the uniform magnetic field. Okay. Make a note of this.
Can you explain how F is equal to mv square by r?
mv square by r is the centripetal force, ma. That is a formula.
Okay.
Got it, Vaishnavi?
Yes, yes.
Yeah.
Sir, can you go to the previous slide?
This one only, no?
To the previous one.
Previous is something I thought I already discussed, so I didn't show it. Maybe you can just take a screenshot of that. You can concentrate on the second slide. Let me know once you're done.
They are done.
Yes, that's what the mathematical equation. Because it is uniform mathematics. It had been non-uniform. That time was but the path does not change. So there are two things you are getting that question. Here it is uniform and force is by default perfectly constant. So because these two things are falling in place, it is uniform separation. Had it been a non-uniform magnetic field, then also what the one reality force would have still be perpendicular to magnetic field. What would have happened to magnetic field? It is not in the same direction everywhere. It is gained from position to position, due to which the path of the particle will normally uniform circle, be some exact pattern, depending on how that changes. Because this both being perpendicular to magnetic field has nothing to do with whether magnetic field is uniform or not. It is always. Why is it? Because it's something that's not something that you are doing. At the same time, that means left hand is also supporting you. Yes, sir. Yes, sir. Now the next question is. Now the next question is, we know that the particle is going to revolve in a circular path. So it takes some time for the particle to complete the circular path. Right? What do you call the time as? Time period. Right? So if I put a question of what is going to be the time period of revolution, what will the answer be? So time is equal to the total distance traveled divided by speed. So if I take this is r and this is v, r and v are perpendicular to each other in circular motion, right? So time is equal to how much time does it, how much is the distance covered by the particle in one full revolution? It is 2 pi r divided by what is the speed? V. So it is going to be 2 pi into r is mv divided by qb, the whole divided by v. So v and v will get cancelled. What will the answer be? It is going to be 2 pi m divided by QB. Here, there is an important point to be observed. What is it? If you observe the time period, it is independent of velocity. So it is independent of velocity. So it is independent of V. So what is the meaning of it? With whatever speed you put the charged particle into revolution, into a circular motion, it will complete the whole revolution at the same time, provided it is the same charged particle and the same magnetic field. So what will happen here is, since R is directly proportional to, or R is equal to mv divided by qb, if you increase the speed of the particle, listen to this carefully, if you increase the speed of the particle, radius of the circular path will increase. Though the radius is going to increase, what will happen is the time it takes to complete the revolution will be the same. If you project it with lesser speed, right? If you project it with lesser speed, it will try to maintain the same time period by adjusting the radius. So that is the meaning of this word. It is independent of velocity. We should not immediately think that here R is directly proportional to V. It will take a bigger turn. If it takes a bigger turn, how is the time period going to get balanced? No. So depending on the speed with which you project, the radius will be adjusted in such a way that the radius will either be big or small, right? And it will ensure that it completes the revolution in the same amount of time. That is an important observation from this, right? Time period is independent of velocity. So from here, what I can do is I can define the concept of frequency, which is given as the number of revolutions per unit time, which is also 1 by time period, which is given as QB divided by 2 pi m. If you observe, the frequency is also obviously independent of velocity, right? And this frequency is generally given a name called as cyclotron frequency. See, cyclotron is a device, right, which is used to accelerate the charged particles, right, about which we'll discuss later. So this frequency name is called as cyclotron frequency. I hope I'm clear, right? You understood how to calculate time period and frequency, right? So make a note of this. Those are online, any doubt? Those are online. Am I audible?
Yes, sir.
Any doubt?
No, sir.
Okay. Then we can wind up.
Thank you, sir. Thank you, sir.